Question 1. An employee work in a plant with a FAR of 4. If this employee work a 4-hour shift, 200 days per year, so what is the expected death per person per year? So this is very straightforward. We can straight away go back to the formula booklet and get the formula of FAR out. So we are going to write it down here. So FAR is given as number of fatality times 10 to the power of 8 and total hour work by all employees. Okay, so first of all, we may want to look at how do we get the 10 to the power of 8 here. So in case you can't remember, so for the FAR calculations, they assumes that, or not to say assume, the calculations take into considerations of 1,000 workers in the similar workplace and assuming that they worked 50 years in their lifetime. And with that, also we look at the normal work hours, which is 40 hours per week and 50 weeks per year. Okay, so remember we only take into considerations of 50 weeks, even though 1 year we have 52 weeks. 52 weeks per year, but we have to minus 2 weeks of annual leave. So this will give you 50 weeks per year. Okay, so we have this value given, we can calculate this. So now we want to find what is the expected death per person per year. So in that case, first I will calculate out the total hours work. So it's given this operator work 4 hours per shift and there's only 1 shift a day, and also they works 200 days per year. So in 1 year this person work 800 hours per year. So now we have this FAR values, which is given as 4, and now we have this value. So the number of fatality is, then look at the formula, is FAR number times the total hour and divide by 10 to the power of 8, in this case 4 times 800 to the 10 to the power of 8. You will get the answer of 3.2 times 10 to the power of -5 death per year per person. Okay, so you get the answer here. Okay, looking at question 2 right now. So we have 3 process units in the plant and each of them has FAR of 0.5, 0.3 and 1.0. So let's draw them out. So we have 1, 0.5, equipment 2, 0.3, and the last equipment 1.0. So A, what is the overall FAR of the plant assuming the worker exposed to all 3 units simultaneously? So over here you have operators exposed to all 3 at the same time. So the FAR, very straightforward. All you have to do is add up all the FAR values for 3 equipment. So 0.5 plus 0.3 plus 1.0. So you will get 1.8. Okay. So, but now assume that the units are far enough apart that an accident in one will not affect the other. So meaning they are so far away. Let me split them up. So in that case, I will not need this. Okay, let me change to another color. And So if the worker spend 20% of the time here, so this is B, 20% of the time in A, and 40% of the time in area 2, and also another 40% of time in area 3. So what is the overall far for this operator? So now you have the operators move around in area 1, 2, 3. Okay, so the overall far would then be separated. So meaning you have 20% time that's spent in area 1, which the far is 0.5, plus 40% times in area 2, so you get 40% times 0.3, plus a 40% at area 3, so 1.0, and then just write it out in the correct mathematical equation. So with this, if you calculate out, I think you will get something like 0.62. So you can see this value versus this value here. Just by separating the units apart, we immediately reduce the far values of the operator exposure from 1.8 to 0.62. So there are few ways we can do this. Either we put up a partitions like what I did here, or we put the equipment far apart so that they would not affect each other, even though they have the same far value of each individual equipment. So with that, you know what to do if you are given the job to reduce the hazard in your workplace. Chapter 2, question 3 of first questions of the chapter 2. Determine the concentrations of ethylene oxide that will cause 50% fatality. So let's draw this down first. We are looking for ethylene oxide. That if the exposure occurs for 30 minutes, so meaning if we have T equals 30 minutes, and we look at the probability of 50% fatality. So this one go back to the probability equations where you're going to use table 2.4 and table 2.5 to run this calculation. So have your data formula and data handbooks ready. So let's take a look at this handbook. So I have uploaded this booklet. I call that a handbook because it's really useful. And in time, so you have to download the copy, and the hard copy will be given for your final exam. So get yourself familiarized with the booklet and to see what is inside here, what formulas are given, etc. So you can see from here, we are going to use a probability equations here. Given here, y equals to k1 plus k2 ln v. So, and we are also going to use table 2.4, 2.5 to look for the data that we need. Okay, so let's go all the way down to table 2.4. So this table we are going to use 2.4, 2.5. Okay, so let's go back to the question first. So just now we look at the formulas. It is y equals to k1 plus k2 ln v. So from table 2.4, so y value we can get it from table 2-4 at p equals to 50%. So let's take a look at table 2.4. So here we are. So P, these are the P value. This percentage here is the percentage of be it fatalities or anything that for us to calculate the probit value. So 50%, 5, 0. So this is our Y value. Okay, so the Y value, the probit value here is 5.0. So let's put it back here. this is 5.0. Okay, so now we want to find out what is the K1 value, K2 value, and V values, and these three values can be taken from table 2-5. So let's take a look at table 2-5 here. We are looking for, what was the chemical again? Ethylene oxide. We are looking for ethylene oxide. So go to table 2.5, look for ethylene oxide. Yep, I think we found it here. You can see ethylene oxide depth. Okay, and as we said that this first value here, this is the V value, and we have our K1, K2 value here, so this is the V, which is a summation of C to the power of 1 times T, and K1 is negative 6.19 and K2 is 1.20. In case you're wondering what is C, what is T, you can go all the way down here and you'll find it's written here. C is for concentrations in ppm, and T is time interval or time of exposure in terms of minutes. So if we are going to put all this value back into our formulas, so we will have Y equals to negative 6.19 plus 1 ln summations of C 1.0 T. So in this case, we have 5.0, okay, negative 6.19 plus ln to the power ln to 30 C, since T is already given at 30 minutes. Okay, so when we rearrange this formula, so you get ln 30C equals to 5.0 plus 6.19, we get 11.19. So when we move this 30C, you will get e to the power of 11.19. So in other words, you get, if you put in your calculator, you will get something like 72,403. Therefore, your concentrations of exposure is 72,403 divided by 30. And in this case, you have 2413 ppm. So what does this mean? Okay, so in this case is where at the concentration of 2413 ppm of ethylene oxide in the air, and if the people get exposed to a duration of 30 minutes, the fatality is expected to be at 50%. So meaning in that case, if let's say we look at this value as an engineer, we want to either reduce this concentration, let me use a different color, we either need to reduce these concentrations or we want to reduce the durations of exposure so that we can reduce the percentage of fatality. Question 4. Use equation 2.7 to convert TLV in ppm to TLV in mg per meter cube for benzene, carbon monoxide, and chlorine. So very simple. Even the TLV, TWA values has been given, and it asks to assume the temperature is 25 degrees Celsius and 1 atmospheric pressure. So let's go back to the handbook. As we can see, the formula to convert from ppm, here you go, from ppm to milligram per meter cube. So let's write this formula down in here. So we have concentrations in ppm equals to 0.08205, and we have temperature over pressure and molecular weight, and this is in the unit of mg per meter cube. Okay, so if we want to have the concentrations in mg per meter cube, so we will then just put everything here. So we will have concentrations in ppm times divided by 0.08205. That's the first thing. And then we will have our pressure up, this one pull up. So pressure is 1 atmospheric pressure over temperature 25 degrees Celsius, but the temperature here is in Kelvin. So 25 past 273, you get something like ppm. And oops, I have this atmospheric pressures, and also I need the molecular weight. Okay, so again we have 0.08205 divided by times 1 over 298, this one in atm, this one in Kelvin, times molecular weight. So if we are to put everything down, then you will have 4.090 times 10 to the power of negative 2 concentrations in ppm, times the molecular weight of your items. So that's the formula. So what we are going to look at here, we are looking at benzene, we are looking at carbon monoxide, and we are looking at chlorine. So if I'm to write this chemical down, so I have benzene, I have CO, carbon monoxide, and I have chlorine, Cl2. Okay, and what I need is the molecular weight here for each individual, and also if I were to calculate the TLV, because it asks to convert TLV, so I need to know what is the TLV in terms of ppm here, so that I can do the conversions, and then I can do the TLV conversions in terms of mg per meter cube. Okay, so let's take a look back to our where do we find all this value? It is in the booklet, so don't worry, just go back to the booklet. Oops. Okay, scroll all the way down until you find the threshold limit value data. So this is 2.4, 2.5. No, this is probably equations. We have a lot of data in this booklet. That is why I'm asking you to get yourself familiarized with the data here, so that you know where to get your data. Okay, go down further. And by the way, just since we are here, don't have to worry about conversion, because conversions data are given in terms of volume, everything, in terms of linear measurements, pressure, or even the ideal gas constants are given. So basically all the things that you need to know are given. You just need to know how to apply them. And I have this saturated data. Nope. I want to go to threshold limit value. So continue to scroll down. Oops. Continue to go down until you find, okay, here we are. We have this threshold. Oops. We have this threshold value data. Okay, so we have our TWA, and at the same time, because we need to use that to calculate, so your molecular weight is given here. So we are looking for three elements. One is benzene, so let's find out where is benzene. Benzene's here, okay, and we are also looking at carbon monoxide, and also we are looking at chlorine. So oops, once you have the data, you convert the data back. So we need the molecular weight, 78.11 for benzene, and the TLV TWA is 0.5, and carbon monoxide, the molecular weight is 28.01, and this is the TLV TWA, so we have this value. Let me just point it out so that we know these are the values we look at. So molecular weight for chlorine 70.91 and TWA is 0.5 ppm. So let's convert all this data back to the table that we draw out. So now we have 78.11 and the TLV here is 0.5 ppm. So, and here we have 28.01 and the TLV value here, TWA value is 25, and we have 70.91 here, and this is 0.5. So we can do this separately, no issue. So all you have to do basically is to put this value in here, 4.09 times 10 to the power of negative 2 times 0.5 times 78.11, and you will get the answer. So for this answer, we are getting 1.6 here, and if you do the calculations, you will get 29.6 here, and if you put in back to the same formulas, you will get something like 1.45 here. There you go. Conversions done. The next questions: calculate or determine the potential depth resulting from the following exposure to chlorine. So we have a series of exposures. First, the person is being exposed 200 ppm for 15 minutes, followed by 100 ppm for 5 minutes and 50 ppm for 2 minutes, and the chemical here is chlorine. So we want to calculate what is the potential fatality. And the easiest way to do this is to draw a table, yeah, to put out all this value here. So we want to find out what is the concentration, ppm here. So we have 200 ppm, and we have 100 ppm, and we have 50 ppm here. And so what the next thing is, we want to know what is the exposure time as well. So T is 15 minutes because, okay, and this is 5 minutes, and this is 2 minutes. So let's take a look at the booklet because we want to find what is the probability equations for this one. So remember, just now we talked about y equals to K1 plus K2 ln V. So you can't remember these formulas, it is again given here in the probability equation. Yep. Okay. So let's go to table 2.4 and 2.5 to see what are the data that we need. So let's take a look at 2.5 first. So we are talking about chlorine depth. So look for chlorine, it's over here. So you have a V values of summations of C to the power of T at C to the power of 2 times T, and K1 is negative 8.29 and K2 is 0.92. So let's translate back to the equations we have here. So we have K1 negative 8.29, K2 we have 0.92, and then we have summations of C to the power of 2 here and times T. Okay, so in that case, our equations is negative 8.29 plus 0.92 ln summation c square t. Okay, so in that case, if we come back to this table, so we will need c square because the formulas here returns we need c square. Okay, so let's take this. So c to the power of 2 will have 4.0 times 10 to the power of 4. Just 200 times 200 will get you 40,000. And then we have 100 to the power of 2, so you will have 1.0 10 to the power of 4 as well. And then we have 50 to the power of 2, you will have 2.5 times 10 to the power of 2. Oh, sorry, 10 to the power of 3, because 50 times 50 is 25, so it's 2500. Okay, so now we have c square t. So this one times this one. You get something like 6.0 times 10 to the power of 5. Yeah, am I correct? Yes, I think so. And then we have 5.0 times 10 to the power of 4. And of course, the last one, when we times this one, so you get again 5.0 times 10 to the power of 3. So your total summations, which is this value, you have to add all three up. You get something like 6.55 times 10 to the power of 5. Okay. So now we put in all our values here. So we get negative 8.29 plus 0.92 ln 6.55 times 10 to the power of 5. Okay, in this case we get something like 4.03. Okay, so now we want to find what is the potential fatality rate, P, or we call the fatality rate, T percentage. So this one we have to refer back to table 2-4, looking for value 4.03. So let's come back here. Okay, so we have values 4.01 here, 4.05 here, so we have to interpolate between these two. So we have it between 16 to 17%, because here is 10, so it's between 6, 7, so roughly about 16.5, because since it's right in the middle. So the probability fatality rate here estimated to be around 16.5%. And there you go. So with the exposures of this to chlorine at this series of concentrations, let me put a different color, from 200 ppm 15 minutes to 100 ppm 5 minutes to 50 ppm 2 minutes, the expected death percentage is at 16.5%. So now question 6. Determine or calculate the duration times in minutes in which a group of 100 people can be exposed to 1,500 ppm of carbon monoxide that result in 0% fatality. Okay, that's number 1. And number 2, that results to 50% fatality. So first, take a look at the Probit equations here. Again, y equals to K1 plus K2 ln V. So let's take a look at what are these K1 value, K2 value, and V value for carbon monoxide. Yeah, we want to focus on carbon monoxide. So go to this table, look for carbon monoxide. And there you go, it's here. Okay, so V value, summations of C to the power of 1T, K1 value negative 37.98, K2 value 3.7. So let's translate all this data back to the formula. So we have Y equals to negative 37.98 plus 3.7 ln CT. I don't need the summations here because since we're talking about single digit here. Yeah, so what we want to find out here is what is T. We want to find out T. So straightforward. So we want to next find out what is our Y value. So A, when P percentage is at 0, what is Y? Okay, so let's take a look back at this table 2.4. So you see, over here, if we are talking about 1% death, we are looking at the Y value of 2.67. So in that case, we are assuming any value that is lesser than 2.67 is the value that we can use. So meaning in this case, if we want to talk about 0%, we look at 2.66, because when we look at 0, for example, then you can't do any calculation because there's anything between 0 to 2.66, the results will be 0% fatality. So we get the highest value. In this case will be 2.66. Yeah, so we put that back. So the Y value here is 2.66 to do the calculation. So meaning this is the maximum duration that the people can be exposed to, T maximum, when P equals 0%. Okay, so simple. 2.66 equals to negative 37.98 plus 3.7 ln 1500T. Okay, same thing with our calculations just now. So you get something like 1500T equals to e to the power of what is that, 2.66 plus 37.98 divided by 3.7. Okay, so in that case you get something along the line of 5.87 times 10 to the power of 4. So if we put this down, T equals to 5.87 times 10 to the power of 4 divided by 1500, you get along the line of 39.1 minutes. Okay, so meaning maximum exposure in this case to result for 0% fatality is at 39.1 minutes. Means any exposures more than this, they might start to have people dying in that area. So the maximum exposure will be 39.1 minutes. That's for part A. So for part B, we are looking at P equals to 50%. Okay, so again, go back to this table when P equals to 50%. So use a different color. P at 50%, our probability equations is at 5. So meaning y equals to 5.0 from table 2.4. So again, put that back into the formulas, same formulas. So instead of 2.66, now you can 5.0 equals to negative 37.98 plus 3.7 ln 1500t. And so I think with that you can calculate what is t. So 1500 t is e to the power of 5 plus 37.98 divided by 3.7. So there you go when you do your calculations in terms of minutes. If I'm not mistaken, it is about 73.9 minutes. Okay, there you go. Solve the issues here. So meaning if let's say the exposure is up to nearly 74 minutes, we are expecting the estimated death rate for this exposure to this carbon monoxide at 1500 ppm will be around 50% death. So the next questions. Estimate the exposure concentrations in ppm that will result in fatality of 80% of the exposed individual if they are exposed to phosphine for 4 minutes. So just now we were looking at the durations at a given concentration. So now we want to find by given durations what is the concentrations that will result in 80% death rate for phosphine gas. So T is 4 minutes. So again, go back to the same probability equations. Y equals to K1 plus K2 ln V. So now go back to table 2.5 to find out what is the K1, K2 value. So for phosphines, we have it here. So again, V value is C to the power of 1T, and K1 value negative 19.27, K2 value 3.69. So let's put that value back. So we have negative 19.27 plus 3.69 ln CT. So we have 4C here. And also we want to find out what is our Y value. So Y value can be getted at P 80%. So go to table 2.4. So back to table 2.4. So at 80% death rate, so P value is 5.84. So that will give us the value of 5.84. So put this into the value. So 5.84 equals to 19.27 plus 3.69 ln 4C. So in that case, ln 4C, we have 5.84 plus 19.27 divided by 3.69. We get something along the line of 6.80. So 4C e to the power of 6.8, and we get something like 897.85, and therefore our concentrations here is at 224.5 ppm. So in conclusions, if the people's being exposed to phosphine for 4 minutes at 224.5 ppm, we are expecting a death rate of 80%. So that concludes the tutorial for today. Thank you very much.